Alright everyone, it's Mr. Rooney back with yet another video. Today guys, we're going to be talking about topic 6 of Unit 7, which is finding the equilibrium concentrations. Okay, so briefly in this unit guys, if you recall, what we've been involving our calculations with, specifically with the equilibrium constant K, is we've been given those equilibrium concentrations at equilibrium, or we've been given enough information in the problem to find them, so we can then go and calculate the equilibrium constant. Now, in terms of this section, what's going to be given to us is just the initial concentrations and Kc, and we're going to be asked to find those equilibrium concentrations. So it's kind of just putting topic 4, but it's kind of flipping it on its head is the easiest way I could explain it. Now, in terms of what we need to find an equilibrium concentration, very simple. You need a balanced chemical equation. You need to write the equilibrium constant expression. We need the equilibrium constant, and we just need the initial concentration of something, okay? The rest we can use stoichiometry, plug those values into that icebox in terms of x, and then solve for x. Now, where this subsection is going to take a more turn in just a slightly more challenging is we might have to use the quadratic equation from math class here. So let's just dive into an example problem. All right, and we've got 0.50 moles of HI is placed in a flask of 5 liters, and then it tells us that Kc is 0.016. Find the equilibrium concentrations of all species. All right, so the first step, guys, that I like to do is just briefly ensure that our chemical reaction is balanced, and you'll notice that it is, right? We've got 2 hydrogen on both sides of the equation, as well as 2 I's on both sides of the equation. So our chemical reaction is balanced, so we can proceed to writing our equilibrium expression, right? So our equilibrium expression, of course, is Kc is equal to the products, right? So H2, concentration of H2 times the concentration of I2 raised to their stoichiometric coefficients. Well, they're both 1, so we don't have to worry about it. Divided by the concentration of the reactant. So in this case, HI raised to its stoichiometry coefficient, which is why we're going to square it. So we have our first step already done. We have our expression for Kc written. Now we got to construct an icebox. So initial, change, equilibrium, right? And I'm going to briefly just set this up as well as convert our 0.50 moles into molarity of HI. So I'll be back in just a moment. All right, guys, so as you can see, my icebox has been constructed. I took 0.5 moles in our 5-liter flask and converted that into molarity, which would be 0.10 molar. Since there is no information given to me about the products, we can assume that we have 0 as our initial concentration for both of our products. And now, guys, we're going to construct the icebox just like how we learned in class today when we were calculating the equilibrium constant. So in other words, I'm going to solve this in terms of x. So we're going to subtract 2x from HI because that's a product. I'm sorry, that's a reactant. It's being used up. So we're going to do 0.10 molar minus 2x. And then here we're going to add x because there's a stoichiometric coefficient of 1 in front of H2. We're going to repeat that same idea for I2, right? So since there's only a 1 in front of here, it's just x. Now, guys, we have our equilibrium concentrations, right? So we've got 0.10 minus 2x for the equilibrium concentration of HI, and then x for both H2 and I2 respectively, okay? We're going to throw these values into our equilibrium expression now and solve for x. So we're going to say, okay, 0.016, that's our equilibrium constant, is equal to, well, if I put x times x in, we know that's just going to be x squared, right? So x squared's up top because this is x and this is x, right? And we're going to divide that by 0.1 minus 2x squared. Now, this is the part, guys, where you may have to do the quadratic. In this particular problem, though, we're going to get out of it because if you're paying very close attention, right, I could take the square root of both sides of my equation and clear x squared as well as this second power here, right? Because the x squared on top, I've got raised to the second power in the denominator. So if I take the square root of both sides, I can clear that out of there. And that's exactly what I'm going to do, because who wants to do the quadratic formula if we don't have to? When we do that, guys, we're going to get 0.13 is equal to x divided by 0.1 minus 2x. Now from here, guys, all we're doing is solving for x. So I'm going to move this out of the denominator and I'm going to distribute 0.13. When I do that, I get 0.013 is minus 0.26x is equal to x. So again, guys, how did I get this? As I just multiplied the denominator of both sides of my equation. So 0.1 minus 2x times 0.13, and then I multiplied that over here. When we do that, in order to solve for x, I gotta get my like terms on one side. So we're gonna have 0.013 is equal to 1.26x, and then x is going to equal 0.010 molar, since that's what we're looking for from equilibrium concentration here. So this is x. Okay, so 0.01 molar. Now, it's super important, guys, that you plug x back into our expressions at the equilibrium concentration. So our equilibrium concentration for I2 is 0.01 molar, as well as our equilibrium concentration for H2 is 0.01 molar. However, you got to plug x into 2x here, and when you do that, 0.1 minus 2 times 0.010, you should get 0.08 molar. Now, these are your answers that you want, but because, you know, this is, we have reached the end of the problem, we want to show our, you know, whoever's grading it, me, your future chemistry professor, the AP examiners, you want to, you know, come out and state what's what. So HI's concentration, and this is of course at equilibrium, that's what's going to follow. The most appropriate thing to do is to just go out and list it, that we've got 0.08 molar. H2's equilibrium concentration is 0.010 molar, and I2's concentration is 0.01 molar. Don't forget to include your units. Don't forget to plug these values and state what you've got. The most common mistake, guys, is forgetting after you solve for x and have what your change is, forgetting to go plug that back into your equilibrium concentrations within your icebox. So don't forget to do that. All right. With that said, I'm going to do another problem with you. So let's go ahead and do it. This one says we've got 0.1 moles of N2O4 is added to a liter vessel. If Kc is 0.36, we need to find the equilibrium constant of both species. All right, so diving into this one, we're going to, of course, construct our icebox. So I'm going to pause the video, and I'll be right back when I have it. All right, guys, so for my icebox, I got 0.100 molar for our concentration of N2O4 and 0 molar for our concentration of NO2. Again, guys, if they don't give us anything about a product, or for that matter, a reactant, we, of course, assume the initial concentration is, in fact, 0. Now, I did jump the gun ever so slightly here. I forgot to write my equilibrium expression. So Kc is going to be the products, so the concentration of NO2 raised to its stoichiometric coefficient, in this case to the second power, divided by the concentration of our reactants. In this case, it's N2O4, raised to no power there. And then, guys, we got to fill out the icebox, right? So in terms of the icebox, we're going to subtract x from our reactants because there's a stoichiometric coefficient of 1 there. So 0.100 minus x is our equilibrium concentration of N2O4. For N2O, for NO2, we're going to add 2x because we have a stoichiometric coefficient of 2 here. And at equilibrium, its concentration will be 2x. So now, guys, we're ready to plug these values into our equilibrium constant. So I'm going to have 0.36 set equal to the concentration of 2x, and we're going to square that. And then we're going to divide by 0.100 minus x. We simplify this ever so slightly. We're going to get 4x squared on top, divided by 0.100 minus x. Okay. Now, guys, we got to proceed to get our values. We got to clear x out of our denominator here. When I do that, we will get 0.036 minus 0.36x, right, is set equal to 4x squared. Okay. Now I'm going to try to get this equation to look like a quadratic equation. So in other words, I'm going to move everything over to one side. So we're going to have 4x squared plus 0.36x minus 0.036 is equal to 0. And again, the whole point of this was to get this equation to look like the quadratic quadratic equation, right? Now, from here, guys, this is where we have to use the quadratic. So this is x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. Okay, so again, this is the whole reason why you learn about the quadratic formula in math class is, of course, to use it in chemistry. Like, why wouldn't it be that the case? Okay, so remember, guys, your coefficient in front of x squared is in fact a. Your coefficient in front of your linear variable, in this case x, is your b, and then with no variable, c is your constant, right? So when we plug this in, we're going to say x is equal to the opposite of 0.36 plus or minus the square root of b squared. So in this case, it's 0.36 squared minus 4 ac, which is going to be 4 times 0.036 all over 2 times 4. Okay, and then you're going to solve for x. All right, so go ahead, plug that number into your calculator. You should get x is equal to 0.06 molar. Okay, now you'll also get a second root because, of course, a quadratic formula has 2 correct answers, right? It has a positive root and then it has a negative root. Well, obviously in chemistry, we're not looking for any negative concentrations. Our concentrations are positives. So we always inherently go with the positive concentration. All right. So that's why I didn't even put here the negative root that I got after I plugged in everything into the quadratic. Now, with that being said, this is the value of x. That is not our equilibrium concentrations. Make sure you remember that, guys. Again, the most common mistake is forgetting to go back here and plug x in for our equilibrium concentration. So our equilibrium concentration of NO2 is going to be 0.12 molar, and our equilibrium concentration of N2O4 is 0.04 molar. Again, it's a good practice to just, N2O2 equilibrium concentration and the concentration of NO2 equilibrium concentration. So again, at equilibrium, just quickly note to the side that you know the difference here and you've plugged in your numbers after you got back to the icebox. It's always just good to come back and label it Leave no room for the imagination for the person who's grading it, that you know that the concentrations are 0.040 molar for N2O4 and the concentration of NO2 is 0.12 molar. And this is our final answer. All right, these numbers here. Again, guys, most common mistake is to just solve for X, but X is just your change in the equilibrium. It's not actually your correct answer. So don't forget to plug X in into your equilibrium concentrations within the icebox. All right. Let's do one more example for today, and then we'll be finished this video. All right. Here is an example problem, but this is you do, we review. So it says 0.800 moles of Br2 is put into a 2-liter vessel. If the equilibrium constant is 1.04 times 10 to the negative third, I want you to find the equilibrium concentration of both species. So go ahead, guys, do me a favor, pause the video, and try this one on your own. All right, everyone, and I hope you were able to get the concentration of Br2 should be 0.390 molar, and the concentration of Br should be 0.0202 molar at equilibrium. As you guys can see, my work is shown here. You do need the icebox. You obviously need the equilibrium expression, and then you of course set the equilibrium constant, in this case 1.04 times 10 to the negative third, equal to in my case 2x raised to the second power divided by 0.400 minus x. In other words, those equilibrium concentrations from the icebox. You do need in fact need the quadratic. As a reminder, I'm only showing you the positive root, right? Because a quadratic formula will give you both a positive root and a negative root when you solve for x. Again, in chemistry, we're only interested in the positive root because, of course, you can only have a positive concentration. And then I plug that back into my equilibrium concentrations here. And that's how I got 0.390 molar for Br2 and then 0.0202 molar for just Br. Now, the one thing that we can address real quick, guys, is there a way to check your values for the equilibrium concentrations? Indeed, there is. If you plug your equilibrium concentrations into your Kc expression, so I'm talking that right here, you should get the value of Kc given to you in the problem if you did the math correctly. So if you plug in 0.390 molar for Br2 in the denominator, and then you plug in 0.202 into the numerator and square it, you will get back 1.04 times 10 to the negative 3. That's just a quick way to check your work. Of course, we could have checked our work just like that on example problems 1 and 2. And with that being said, guys, we're going to spend all of class just practicing finding equilibrium concentrations. But in the meantime, if you do have a question, please feel free to send me an email.